like this. Now we can draw a tangent line on here. That tangent line will be above the ground. Any questions about that? Yeah.
Both of these are concave.
These are, well, concave just means curving. So as long as they're curving in some direction, then they have concavity. It's just whether it goes up, like an umbrella, like a U shape, or it goes down like an umbrella. Okay. Now, it doesn't have to complete the entire U shape here or the entire umbrella. If we only had a piece of it, say we only had something like this, is that concave up or concave down? So is this a piece of a U shape or is this a piece of an umbrella?
Shape U.
This is a piece of a U shape, so this would be concave up. Okay, so it doesn't have to make the full U shape or the full umbrella. As long as it's part of it, then that's okay.
So which one is it? Which one of them you said?
So which one is this one going to be?
U.
What? So it's like a U shape, which is
Down.
concave up, up like a cup. Looks like a cup. Looks like a cup. It'll hold water.
Okay.
That's going to be concave up.
Okay.
An umbrella that's going to push water out to the side, that's going to be concave down. Okay. So these are both up. And the words up and down each have a letter that is the correct shape. So the U here is the shape of a concave up, and the N is the shape of a concave down. So let's look at a graph here and pick out the regions where it's concave up and concave down. So here's a graph, and we want to know on the regions of this graph, where is it concave up and where is it concave down? So what about this region from A to B? Is that concave up or concave down?
Concave down.
That's concave down. It's curving back towards the ground. B and C?
Concave up.
That's concave up. What about C and D?
Down.
Concave down. Does everybody see that? D and E?
Up.
That's concave up. E and P, I don't know why they use P there. E and P,
Up.
that's up. And P and Q
Down.
is down. Okay, so we have down, we have up, we have down, we have up, we have up, we have down. Okay. Everybody okay with that? Seeing what concave up and concave down looks like? Okay. inflection point is a place on the graph where concavity changes directions. Where it changes from up to down, or where it changes from down to up. Okay, so where would our inflection points be on this graph?
B.
B, does everybody agree that B is an inflection point? Yeah, because at B it changes from down to up.
C.
C changes from up to down.
D.
At D it changes from down to up.
And then E.
What about E? Does it change at E?
Maybe not.
So it goes from up to up at D. It's an interesting thing is happening at E, but the concavity doesn't change there. So that's technically not an inflection point.
Because it's both up.
It's up on both sides of it. It has to be different on either side of it for it to be good. What about P?
Yes.
Yeah, P is an inflection point because it does change there. Okay?
So it wouldn't be A and Q, right?
Yeah, and A and Q are the endpoints. There's nothing to change at the end of it at the end. So, okay. So the inflection points are so the note I want to add to this. So the inflection points have to happen where the second derivative is 0 or does not exist. Okay? Now, what are the points called when the first derivative is 0 or does not exist? Those are the critical points. So when the first derivative is 0 or does not exist, those are critical points. When the second derivative is 0 or does not exist, that's where we get the inflection points. Does everybody see that? Because if it's going to change from down to up or up to down, we're going to see that anytime it changes, the second derivative, it has to be 0 or has to not exist. So these are equivalent. So inflection points are like critical points, but with the second derivative. Instead of the first derivative. So critical points are when the first derivative is 0 or does not exist. Inflection points are when it's the second derivative. Okay? Are we okay with that? Okay. Okay. So now we want to know, what does the second derivative say about concavity? And it says if the second derivative is greater than 0 at a point, then the curve is concave up at that point. Okay?
It's concave up.
Concave up.
That second derivative.
Mm-hmm. And concave down when f double prime of x is less than 0. Okay. So when we were doing increasing and decreasing, we were looking for when the first derivative was positive or when the first derivative was negative. For concavity, concave up, concave down, we're gonna be looking at when the second derivative is positive and when the second derivative is negative. Okay, so the process is gonna be exactly the same as what we did last time, except we're gonna be using the second derivative instead of the first. Does that make sense, everybody? So we're going to take the second derivative, we're gonna set it equal to 0. We're gonna draw the number line and mark off those points. Pick our test points in between, see if it's positive or negative. If it's positive, it's concave up. If it's negative, it's concave down. And then we write out our interval. Does that make sense? Okay. And then we're going to be asking for where the inflection points are. And the inflection points are basically just where is the second derivative equal to 0. But we do have this one little extra thing that the concavity actually has to change at that point. So it has to be different on both sides of that point. So it's a tiny bit different than the critical points, because the critical points, the increasing, decreasing doesn't have to change for critical points for it to be called a critical point, but it does for an inflection point. So sometimes some of our second derivative equals zeros get thrown out because the concavity doesn't change. So we just have to be careful of that. It's rare for that to happen. Usually if the second derivative is 0, usually it changes. Okay, so let's go back to this example here. Oh, this example that I erased. Okay, so we had f of x.
3x to the 4th minus 4x to the 3rd minus 12x to the 2nd plus 5.
That's fine, okay. And so we had f prime of x was 12x cubed minus 12x squared minus 24. And we had increasing
Negative 1, comma 0,
2 to infinity, and decreasing.
negative infinity, and negative 1, and then 0 and 2. Local max 0 and 5, and then 1, negative 1 and 0, 2 and 37. Negative 37.
Okay. So here's our function that we've been working on so far. We found increasing, decreasing, we found local max and min. So now what we're gonna do is we're gonna find concave up and concave down. So we wanna find, and the term for this, intervals of concavity. And so what are we gonna need to do?
Get the second derivative.
We're gonna need the second derivative for this. So just take the second derivative here.
That should be negative 24x.
Negative 24x, thank you. Okay, so this is going to be 36x squared minus 24x minus 24. And what are we gonna do with this? Set it equal to 0, just like we did with the first derivative when we're doing increasing, decreasing. Same thing here, we're gonna set this equal to 0. Factor out a 12, we get 3x squared minus 2x minus 2 equals 0. I think this is gonna factor. Yeah, this one's not gonna factor. So here we'll just use the quadratic formula. So quadratic formula is negative b plus or minus square root a squared, b squared. Over 2a squared. Okay, so we're gonna do 2 plus or minus square root of 4 minus 4 times 3 times negative 2 all over 2 times. So that's going to be 8, 24, 28, all over 6.
So where are you going now? This
Quadratic formula. So when we have a degree 2 polynomial that doesn't factor, We just use the quadratic formula on it. Okay, and so if we evaluate these, what this is, just plug this into the calculator. So we're going to have 2 minus 28 divided by 8. So this is equal to negative 0.548. And 1.215. Okay. So those are our two places where we could have inflection points. We probably have inflection points at those two places. But now what we need to do is we need to set up our number line. So we have negative 0.548 and 1.215. What do we do from here?
How did you get 2 points?
The plus or minus.
Oh.
2 minus that gives us this, 2 plus that gives us this. Okay, after we find our critical points, we set up the number line and mark those off. What do we do next?
Put other points in between.
Pick the points in between. So we have 3 regions here, so we need to pick a point in each region. What do you want to pick over here?
Negative.
So something has to be less than negative 0.548, so we'll just do negative 1 there. What about a point in between? 0. 0 is always a good choice because it's really easy to evaluate at 0. And then out here? 2. Okay. And where are we going to plug these back into? What is it we're trying to determine here?
Derivative.
So what's the question asking for?
Inflection point.
Concave up or down. It's asking for concave up or down, and what function tells us concave up or down? Second derivative. So we need to plug these back into the second derivative. Okay? So those are the functions what the functions are going to be used for. So the original function will tell us where the maxes and mins are. The derivative will tell us where it's increasing and decreasing, and the second derivative will tell us concave up and concave down. So we need f double prime of negative 1. So we're going to plug in negative 1 into this. So this is going to be 36 times 1. Plus 24 is 60, minus 24 is 36. Okay, so in this region, concave up or concave down?
Concave up.
That's concave up. And so I'm going to draw just a picture of concave up there. F double prime of 0. And you could use the table function on this to evaluate these points. It's, you don't have to do these by hand, but F double prime of 0. So that's going to be 0 minus 24. And so in that region, since we got a negative answer, that's going to be concave down. prime of 2. 4 is 8, minus 2 is 6, 12 is 72. And so that's going to be concave up, because we got positive.
What did you plug into the second derivative?
So I plugged in -1 into this,
Uh-huh.
plugged in 0 into this, and plugged in 2 into this. So basically,
Into the whole thing?
into this whole thing.
Not just the 36x.
Right, into that whole thing. So basically what you would do is, on the calculator, type this into your y equals, and then go to your table and do -1, 0, and 2.
Oh, I see, the same way I've been doing it.
Okay. I didn't want to turn the calculator on overhead on the calculator, so I just evaluated. But that's what you would do. So you type this into y equals, plug those into your table, and it'll tell you what they are. Okay. Any questions here? So where are we concave up? Let me add this over here.
-1.
From where to where?
It's infinity, right?
Would be -1 to -0.542.
Those test points will never show up in our answers. Those are just
It's a negative infinity,
negative infinity
and then
to
0.54.
negative 0.548 and
-548.
so we're still up. Still in concave up. Where else is it concave up?
1.2.
1.2 to positive infinity.
1.215 to positive infinity. Concave down is in between. So negative 0.548, 1.215. Okay. And then our inflection points.
The inflection points will be the -1, 0, and 2.
No, those are our test points.
Would be -0.548.
Negative 0.548 and 1.215. Now, remember that these are what we call critical points. If it was the first derivative, for a second derivative, those are the inflection points. The ones that are marking off our number line, not the test points in between, the purple ones there. Okay? Any questions about this? Okay, these are all the things that we are going to determine based off the first and second derivatives. So increasing, decreasing, local max and mins from the first derivative. Well, the first derivative helps us find where the local maxes and mins are, but it's the points themselves are actually the original function. But increasing, decreasing, and local max and mins from the first derivative, concave up, concave down, and inflection points from the second derivative. Questions here? Okay. So what was the function that I gave you guys to work on?
X to the cube minus 3 squared
Minus x
minus 9x
plus
4.
4. Okay, and so we had f prime of x is 3x squared minus 6x minus 9. And this was increasing on what interval?
Negative infinity to negative 1. And then 3 to
Increasing. And we had a local max. And so this is going to be increasing, then decreasing, so -1 something. 9? -1, 9. And then at 3, that's okay, right, negative, that's it. Don't hold it. At 3, negative 29? 23. 23, okay. Okay, so that's what we have so far. So what I want you guys to do is find the intervals of concavity. Do the same thing we just did. Take the second derivative of it, set it equal to 0. You might have to factor this one. Actually, this one's going to be a lot easier because when we take the second derivative, we're only going to get a degree 1 equation. That's going to be a lot easier to solve. So we're not going to end up with messy decimals on this one. We'll probably end up with a fraction, but that's not too bad. So take the second derivative, set it equal to 0, set up your number line, pick your test points on either side to determine on this side is it concave up or down, on that side is it concave up or down. And then we can, once we have that, we can plug your test points back into the, what do we plug the test points back into here?
Second derivative.
Second derivative, yeah. Okay, so go ahead and do that. Not sure what to do? Having trouble stuck somewhere? So what does X have to do? So what does X have to do? To give us 0, what does X have to do?
Equal to 0.
Well, this whole thing has to equal 0, so what does X itself have to be to?
To equal 0? 1.
Here. I think. Yeah.
It's a plus or a minus one,
No, it's just a plus.
because we're trying to make 0 equal to.
We have to
x
make it
equals
equal.
0.
Yeah, so what does x have to be equal when we subtract one, we get 0. What minus 1 gives us?
1.
Yeah.
But, so the 6 though, it's just, don't care about it? Because
Yeah.
it's not in-
Yeah,
it does not
yeah,
match.
so this one, you don't need to necessarily factor it like that, but, because it's only degree 1. But what you did worked,
Plug one. back
Yeah.
in.
it works there, but there's a little bit easier way to do that.
Sarah?
Yeah, we'll do. Okay. So our derivative is 6x minus 6. Okay, and what are we gonna do with this?
Equal to 0.
Set it equal to 0. So now we have 6x minus 6 equals 0. We can solve this. Because it's degree 1, the easiest way to solve it is just add 6 over the other side.
I see.
And so we get 6x equals 6. Divide by 6. And we get x equals 1. So we only have one critical point here. Inflection point is really better. Okay. Okay, and that's at 1. What do you want to pick for our test points? 0 and 2 are good choices. And so we need f double prime of 0. Plugging in 0 into this, we get negative 6. F double prime of 2 is 12 minus 6, gives us a positive 6. So we're down, we're up. And so what's our interval for concave up? 1 to infinity. And we are concave down from negative infinity to 1. And where's our inflection point?
1.
At 1. Yeah.
Which function do you put into the calculator?
For these,
Yeah.
you're going to put in this function. Second derivative. On WebAssign, I think for inflection points, it might ask you for an ordered pair there. How would we get a y value out of this?
Plug it in there after that.
Plug it back into the original function. Anytime we want to find a y value, that's got to go back to the original function. So over here when we did, or here when we did local maxes and mins, we took the -1 and plugged it back into the original function to get the 9. We would do the same thing here if it asked for it. So, I'm not going to ask for it, but the WebAssign might ask for it. So just warning you ahead of time. Okay. Any questions? Is everybody okay with this process?
Are we gonna do any more of this or no?
No, we're gonna move on now. If you want, you can hang out after class and we can do some more. Okay. Okay, so that's it for 4.3. Okay, so what we're gonna do now is move on to 4.4. So 4.4 is L'Hopital's rule. Okay, and so L'Hôpital was, it looks like La Hospital. I know that. It does. It's actually the French word for hospital, so. But it's pronounced L'Hôpital. One note about the spelling of his name is the spelling of that sound, the L'Hôpital sound, the O sound in there, has changed in French since he was alive. Now, the current spelling of it would be just an O with 2 dots above it and leave the S off of it. And so sometimes you'll see it spelled either way. So sometimes you'll see it with the S, sometimes you'll see it without the S. Both of them are considered correct. So, but this is how he spelled it in his time. So. Okay. And L'Hôpital's rule is a way to find limits. Okay, so we found limits way back in chapter 2, and when we got 0 over 0, what did we do? So when we were first, what's the first thing we always do with limits? We always try.
Plug it in.
Plug it in. We plug it in. And what happens if we get an answer, that's the answer. What happens if we get 0 over 0? That's where we do the factoring and canceling. Okay, and that works great on rational functions, where we can do that. It worked well with the radicals. Sometimes there's a little bit of work, but it worked. But we couldn't do anything with trig functions or exponentials or logs, because those don't work with the factoring and canceling. But L'Hopital's rule is a way to deal with a 0 over 0 case that will work for pretty much any function. Okay? And L'Hopital's rule is stated like this. And the statement of it is more complicated than the actual doing of it. So don't get discouraged if this definition is, or this theorem is, seems overly complicated. Actually, doing L'Hopital's rule is pretty straightforward. Okay. So if the limit as x goes to a of f of x equals 0, and the limit as x goes to a of g of x equals 0, or the limit as x goes to a of f of x equals infinity, and the limit as x goes to a of g of x equals infinity. So L'Hopital's rule actually handles a different case as well. This is going to be the 0 over 0 case. This is going to be an infinity over infinity case. So L'Hopital's rule will handle that as well. Okay. If either of these cases hold, then the limit of this quotient, f of x over g of x, is going to be the same as the limit of f prime of x over g prime of x. Okay? This is the 0 over 0 case. This is the infinity over infinity case. Questions? Let's look at an example of how this works. Limit as x goes to 0 of sine x over x. What are we going to do first?
Check if there's a 0 down, right?
So first thing we always want to check is plug it in. And this doesn't change. still we have to plug in the value first. Actually, it's even more important now than it was before. Because before, when we were doing the factoring and canceling, if it didn't give us 0 over 0, then we would run into a problem with the factoring and canceling. Here, if we blindly apply L'Hopital's rule when we don't have one of these two cases, it'll give us an answer, it'll just be the wrong answer. And that's worse than getting no answer at all, because if we get no answer at all, we know we made a mistake somewhere. But if we get an answer, nothing's telling us that that's the wrong answer. So we have to be really, really careful with L'Hopital's rule that we don't try to apply it when it doesn't match one of those cases. So what do we get when we plug in 0 into this?
0.
Okay, so we get sine of 0 over 0, and sine of 0 is 0, so this is 0 over 0, so this is this case here, which means L'Hopital's rule will apply. Okay, so now this h that I put over the equal sign, it's customary to do that, to put a little h there to let the reader know that you are applying L'Hopital's rule at this step. Because it's not always clear how did we get from this step to this step, because it's not doing algebra. And so the reader, this is just a little hint to the reader of giving them a clue as to what you're doing. It's not required. If you don't put it on there, I'm not going to take any points off, but it is customary, and every author of every textbook I've ever read has always put that H there just to make it clear what's happening on that step of the problem. Okay, so L'Hopital's rule applies, and so now when we apply L'Hopital's rule, what this says is we are going to take the derivative of the top, and we're going to take the derivative of the bottom. We are not applying the quotient rule here. We're not trying to take the derivative of the function. We are applying L'Hopital's rule because we're trying to find a limit. There's a big difference there. So we will not be using the quotient rule when we're using L'Hopital's rule. We do the top and the bottom separately. Okay with that? So what are we going to get when we take the derivative of the top? What's the derivative of sine x? Cosine x. And what's the derivative of the bottom? 1. Okay? And so we have limit as x goes to 0, cosine x over 1. Now what do?
Plug in.
Now we plug it in and see what we get. So we're going to get cosine of 0 over 1. And what is cosine of 0?
0.
So cosine starts at 1, sine starts at 0. So this is going to be 1 over 1, which is 1, which tells us that that original limit was also 1. Okay? Any questions here? Yeah.
What's that H for?
That H is to let you know that we did L'Hopital's rule on that step.
Okay, that's what I was thinking.
Any questions? So these two things are called indeterminate forms. Zero over 0, infinity over infinity. And what that means by indeterminate forms is it doesn't, when we see that case, it means the answer still could be anything. We don't know what it is. It's not determined yet. Okay. Now there are some forms that are determinate. So if we have a number over a number, we'll make the convention that this is not equal to 0, then that's going to just give us an answer. So if we have like 3 over 7, then the answer is just 3/7. If we have 0 over a number, that's just gonna be 0. Okay, so if we have any of those cases, we already know what the answer is. We don't need to apply L'Hopital's rule to it. And actually, we can't apply L'Hopital's rule. If we tried, it would give us the wrong answer. But if you see any of these, we're done. We don't need to do anything. It's when you see these that we can apply L'Hopital's rule. Does that make sense, everybody? See the difference between the two? Recognize them when you see them. Okay. Some important limits that we are going to encounter in this section. Look at that. So those are gonna come into play, and those limits, we're gonna see those. And it's not always immediately obvious what those limits are, but when we see them in problems, we will now be able to go back and reference those. So limit is x, yeah, question?
I'm sorry, why is when you do number divided by 0, why is it not undefined?
It is undefined, but the limit itself will be either be plus or minus infinity.
Oh, okay.
So, and when I say 0 and infinity there, we're not saying that the top actually is 0, we're saying the limit of the top goes to 0. So basically what that really means is the top is really, really close to 0, not exactly 0. Same thing at the bottom is really, really close to 0. And so our fraction is going to have a really, really small denominator, which means the fraction is going to be really big. All of those over there, those are limits to those points. It's not those points exactly. Okay, so here we're taking the limit as x goes to 1 of natural log of x over x minus 1. So what do we do first? Plug in the value. So we get natural log of 1 over 1 minus 1, which is another 0 over 0 case. So we can apply L'Hopital's rule here.
Go back. What did you do first?
First, we plugged in 1
Why 1?
because our limit's going to 1.
Oh, I see.
So we're plugging in 1. So we get natural log of 1 over 1 minus 1. Plug in 1 to that. But natural log of 1 is 0. 1 minus 1 is 0. So this is 0 over 0. Okay. So, so what happens when we apply L'Hopital's rule to this?
We get 1 over x all over 1.
Okay, so derivative of the top, derivative of natural log of x. 1 over x, derivative of the bottom,
1.
1.
plug in and we get one.
What's that?
We plug in and then we get.
And now we plug in 1. Which just is 1. Which tells us that that original limit is also 1.
What we're doing at the, where we have h equal the limit x to the 1.
So this is where that h means we're doing L'Hopital's rule.
Yeah.
So we take the derivative of natural log of x, 1 over x, that's that.
Right.
And the derivative,
1.
x minus 1 is 1. That's that. Okay. Any questions, sir? Okay. So L'Hopital's rule is allowing us to take limits. We wouldn't have been able to do this before with the factoring and canceling. So let's look at another one. So limit as x goes to infinity of e to the x over x.
Yeah, sorry, I have a question. So, at what point do we plug whatever the limit is?
Every time we do a step, basically, we plug in what the limit is to see what we get. So what happens when we try to plug it in here?
We give you infinity over infinity.
So we're plugging in infinity, which basically means we're taking the limit. What it really means is we're taking the limit as we go to infinity. And so that case is this one, so the top is infinity. And x is also going to infinity. So this is an infinity over infinity case. So what are we going to do? We apply L'Hopital's rule. So go ahead and do that. Take the derivative of the top, the derivative of the bottom, and then plug in then take the limit from there and see what you get.
So the first one, the infinity on the top, I get it, why, right? Because that's the e to the x is negative, it's infinity. Why the bottom though?
X is going to infinity, so that x is getting bigger and bigger. That's getting bigger and bigger. This is getting bigger and bigger as well. Okay.
And the limit never changes, right? It's always gonna be.
Always the
infinity.
same. The limit is always, whatever the limit started with, it's going to say that through the whole problem. Okay, so what's the derivative of e to the x?
Yeah,
Same thing. The x. Derivative of x
1.
is 1. And now what happens is x goes to infinity.
Get infinity over 1.
And we just get e to the x, still going off to infinity. So this is infinity over 1, which is just infinity. Any questions there? Okay. Let me give you one to do. Okay, so go ahead and do that one. number over infinity.
Zero. So zero divided by one is just zero.
Right.
So then that's zero.
Okay. So what happens when we try to go to infinity here? What case do we get?
Infinity over infinity.
So natural log of x is going to infinity, so this is infinity over infinity case. And so when we apply L'Hopital's rule, we get what?
1 over x, which are natural log.
Okay, so natural log of x becomes 1 over x. X becomes 1. Now we plug in infinity.
1 over infinity.
Yeah, so we're gonna get 1 over infinity, but we don't really want to write that as what. But what we're gonna have is 1 over infinity over 1, but what is 1 over infinity?
Zero.
So that's 0. And 0 over 1 is just 0. So that tells us our original limit was also 0. Okay? Any questions there? Any questions about L'Hopital's rule so far? Okay, let's go ahead and take a 10-minute break. We'll be back at 10:50, and then continue on with some more L'Hopital's